Hello everyone. Now today in this particular lecture we will be studying about logic gates and few combinational logic circuits. Myself, I am Dr. Sarin Maitri. Logic gates. So today we will be studying about logic gates initially and what is logic gates and how they are very useful in learning electronic subject and also how they are very much useful towards the exam point of view for different board exams regarding the plus 12, plus 11 and all the competitive exams. So now we are going to study about logic gates. Myself, I am Dr. Sarin Maitri. Firstly, we'll try to discuss few lecture goals. Here we'll be discussing about how identifying about few basic gates and describe the behavior of each and every gate, each and every basic gates. Then we'll be describing how these particular gates have been implemented using different kinds of transistors. Later, we'll be combining different kinds of basic gates into build up different kinds of circuits. Then later we'll be talking about the descriptional part of a behavior of this particular gate and or different kinds of circuits which are being usually described with the help of truth tables and logic diagrams. Analog versus digital. In this particular slide, we'll be knowing about what is meant by analog signal and what is meant by digital signal. So first we'll try to know about what is analog signal. Analog signal. Analog signal is the one which has an output that will be usually varying with the particular time. It means that it is a signal which varies continuously with respect to time and also with respect to the input signal which you have given. So that's why we have written here analog signal is the one whose output varies continuously in step with the input signal. So whenever you are giving some input, depending upon the input signal with respect to the step function, it will be varying. That is called as an analog signal. So you can see here usually this is an input signal which has been given over here. The same input signal, depending upon our input signal, either if you are using an amplifier, then definitely what happens, if it is an amplifier, then it will be amplifying the circuit, it will be amplifying the signal which is used for this particular circuit. So you can see here now this particular has been amplification, or else you can see now what is happening here. You are giving some input signal and that the output which you are getting is exactly opposite to this one. Means the input signal is getting inverted. But here there is some kind of amplification is taking place with respect to the input signal, or else we can call it as an this analog signal can be used for different kinds of circuits where you can use it for attenuators, where it's nothing else but attenuation is nothing else but de-amplification circuits, or else you can use it for an amplification circuit. So analog signal is the one which varies continuously in step with respect to the input signal, or else we can simply say it is a signal which varies with the time. Example is this one which we have given over here. The next, digital signal. So here see now, this is the digital signal which you have given over here. The digital signal is the one whose output varies at a discrete voltage. Here discrete voltage means not just like analog. In analog you can see now there is different types of voltages in this particular slot. But here when it comes to the digital signal, the digital will be either it will be at the high state or else it will be at the low state. That means high means it will be treated as a logic 1 in the digital electronics. Low means it will be treated as a logic 0. So now this is a digital signal, this is a logic 0 and this is a logic 1. Your signal will be either in the logic high state or else it will be in the logic 0 state. So that's why digital signal is the one whose output varies at discrete voltage levels, commonly called high or low signal, where high is nothing else but it is called as logic 1, low is called as a logic 0. This is regarding this basic differences between what is meant by analog and what is meant by digital. Now let us see in this slide why do we need actually digital signal. The main reason is that these are the few points which are quoted over here, which are mentioned here. Digital can be used for storage purpose. Whatever the RAMs we are using nowadays in the sophisticated mobile phones or sophisticated laptops or gaming laptops, it needs a huge amount of memory storage element. So these memory storage elements are being designed with respect to this digital electronics procedure only. So in order, we need the digital because in order to store the data, memory characteristics of the digital. Then data can be used in calculation. This digital can be used in calculation. Whatever the computer which knows the language, or the electronic products which knows the language, is a digital language, that is 0 or 1. Your entire the calculations which you do with respect to the calculators will be completely digital calculators. It will be electronic calculators will be of digital signals only. This digital is compatible with the display technologies, compatible with the computer technologies. System can be programmed. This is a very important one. We need a system which can be programmed. If you are not able to program it every time, what happens? It cannot be changed with respect to the technology. It cannot be changed with the ages of the electronics. So in order to go with the age of the new age of the technology or new age of the electronics, we need a programmable device, which means that which we can easily program it every time, we can code it every time, and make it used as per the requirement of that particular time. So that's why the system has to, with the help of digital, the system can be easily programmed. Digital IC families make digital design very easily. So that's why these are the main reasons why we need the digital. The next one, why analog? Most of the real world events are analog in nature. The entire real world events in the particular nature is analog. Just like if you talk about the signals, neural signals which are in the human body, the entire human body consists of the neural signals. These neurons will produce some kind of signals, and these are called as analog signals. These are the electrical signals which are analog in nature. So that's why the entire neural signal, whatever you talk, you name it anything, it is completely, the entire real world events are in analog. So that's why we need the analog. Analog processing is usually simpler. Analog processing is usually faster than the digital, and traditional electronic systems were mostly analog in nature. So these are the few points why we need the analog. Benefits of digital over analog. First one, reproducibility. That's what I told. It can be easily programmable. Digital, the benefits of digital over analog is that we can easily reprogram it or reproduce that one. Not affected by the noise means quality, means when you talk about the noise, mostly in the analog signal, what happens, the noise gets inculcated into that particular signal. It can be any kind of noise. It can be noise due to the environmental part, or it can be noise from the defects of the electronic product. It can be any kind of noise. This noise will be mostly affected with the analog signals, but when it comes to digital, the digital signal will not be affected with the noise. That means that we are going to get better quality of a particular signal over the analog one. Ease of design, data protection, programmable, speed, and economy. So these are the benefits of digital over analog. How it's made. So let us see now how the digital signals are made. Why we are trying to study about digital? Because most of your logic circuits are digital in nature, where we'll be inputting the zeros and ones, high state or low state. That's why we are trying to study about how a digital has been made, how the digital signal has been made. At any point in the circuit, only two voltage states will be there, as I shown you in the previous slide. It will be either in the high state or low state. That is a high state or low state, also sometimes called true or false. In some of the textbooks, instead of giving as a high state, they give it as a true state, true. Instead of giving it as low, they'll be mentioning it as false. It means that it is a high state means logic 1 state, low state means logic 0 state. In the similar way, true means logic 1, false means logic 0. In Boolean logic, it means 0 and 1. Generally, plus 5 volts roughly considered as high state, while 0 volts is considered as a low state, which we usually call it as a ground state. So this is regarding the how digital signals have been taken into consideration. Transistor as a switch is a basic building block of any kind of digital electronics. Transistor is a backbone of any kind of electronic. So with the help of this transistor only we can design any kind of digital electronic products or digital circuits. So this is the transistor symbol you can see over here. These are two different kinds of transistors where this a load is given. One of the transistor is connected, and again here resistor is connected to the base of this transistor. Input signal is given to the base to the resistor, and from the resistor it is given to the base of the transistor. This is the emitter and collector of a transistor. And here it is a VCC. It is a high voltage, and this is a ground terminal which is called as a 0 volts. And this particular transistor will be acting as a switch. Transistor can act as, that's what we have written here. Transistor as a switch is a basic building block of electronic. This can be replaced as switch. If you want to know about this particular concept about how a transistor is working as a switch, you can go back to my videos regarding the electronics in my channel and you can look into that one. I have explained there very clearly in a lecture called Cmos Inverter. In a Cmos inverter, I have explained very clearly that how a transistor will be working as a switch. It means that what happens in the switch can be either in the on state or in the off state. The same on and off state of the particular transistor is explained in a lecture video called as Cmos Inverter. You can go back to that particular lecture. You can look into that one for a better understanding. So this is regarding what is a transistor. Now here, this particular switch is in the open state. Now, this is one of the particular digital electronic product. You can see here now SN74L S00, and this we are supposed to know what is this one. If you look into this one, this is nothing else but it is a Nand gate. You can see here now, this is the Nand gate. This is the structure of a Nand gate. You can see here now different kinds of Nand gates are here. This is how this particular integrated circuit is been made up. This is how the internal part of that particular switch, that particular integrated looks like. This is a pin diagram. It's called as a pin diagram of the NAND integrated circuit. This is 7400 quad 2 input NAND gate. This is a 2 input NAND gate. So now here this inputs have been given here. VCC is there, ground terminal are there, and different inputs have been connected here. The pin diagram of this NAND gate is mentioned in this particular slide. You might have seen the complexity of the particular slide which is changing. You can see now it's a very complex in nature. The similar way, the complexity of digital electronics also looks like. So the complexity in the digital design can be, this complexity can be and generally can be like which actually surpasses the human capability. Why? Because if you look about the present generation of an integrated circuits, there are something like millions of transistors in one particular circuit, one particular integrated circuit. In millions of transistors are there. It's beyond our human capabilities. So that's why I have told the digital design is very complex in nature. You can understand that per centimeter square there are nearly 10 to 100 million transistors. You can imagine how small will be a 1 centimeter square area. In that one particular 1 centimeter square area, there are nearly 10 to 100 million transistors, which are presently happening right now in the VLSI industry or integrated circuit industry. 100 to 1000 million transistors are will be present in the next coming 10 years of age. So now here in the next coming 10 years, you can find this number can go from 100 to 1000 million transistors for the same area of 1 centimeter square. And this complexity provides us a motivation for the computer-based design techniques. So many design techniques are coming up in order to look into this complexity. And most engineering work has been done with the help of the CAD tools. CAD is a computer-aided design tools. Computer-aided design tools. With the help of this design package tools, we can many engineers are trying to solve the complexity of this particular integrated circuit designs. Digital circuits. Now, let us now have a look at the digital circuit. A digital circuit is often constructed from small electronic circuits which are called as a logic gates. So now we are going into the part of our main concept called as a logic gates. So now here, what is logic gates? We'll try to understand in the coming slides. Digital circuit is mainly constructed from a small electronic circuit which is called as a logic gate. Now we have seen already one of the logic gate, that is a Nand gate. Nand gate, in the previous slide you have seen how it looks like, how the integrated circuit of a Nand gate looks like, and how the pin diagram of a Nand gate looks like. Nand gate is one of the logic gate. With the help of this logic gates only we will be constructing the digital circuits. These logic gates are mainly used for the designing of different kinds of combinational logic circuits. Each logic gate represents a function of a Boolean logic. Boolean logic means nothing else but if you talk about one equation like y equal to a plus b, what you are talking about, we are talking about an addition of two inputs, and on the LHS side you have got y, on RHS side you are having a plus b. It means that you are talking about addition of two inputs on the RHS, that is a and b. So when you talk about a plus b, it will be a logic gate called as OR. OR gate, there's a OR gate is mainly used for this additional purpose. So that's one of the example how the Boolean logic equation looks like. A logic gate is an arrangement of electrical control switches, better known as a transistor. So in order to design a transistor, in order to design a logic gate, we need an electronic switch which is called as a transistor. The output of logic gate is an electrical flow or a voltage that is in turn control more logic gates. So now here what does this particular line indicates is that whatever the output comes out from one of the logic gate, that particular signal can be given as an input to different logic gates which are connected to that one in the next level. So that's that's about the output of a logic gate is an electrical flow or a voltage that can in turn control many logic gates. So this output can be given as an input to the different logics in the next level of design. Integrated circuits are the least expensive way to make the logic gates in large volumes. Another form of digital circuit is constructed from the PLD. PLD here means it's a programmable logic devices for small volumes. Why? Because it is much costlier than the integrated circuit, so they don't afford to go for the PLDs in large volumes because of the cost reasons. So that's why they try to construct the PLDs in a small volumes. When the volumes are medium to large, microcontrollers is programmed in order to make an embedded system. So mostly in the embedded system, we will be using a programmable logic devices or programmable logic arrays or programmable array logics. Different kinds of logic devices are there. This have been mainly used in order to design different kinds of microcontrollers, which are the main backbone of the embedded system. So these are usually programmed by the software engineers. So this is how the digital circuit concept looks like. First, we need some small electronic circuits which are called as logic gates. These logic gates have been designed with the help of a switch called as transistors. Again, these logic gates are the main basic backbone in order to design or manufacture or fabricate any kind of integrated circuit which can be done in the larger volumes. If you want the same electronic designs, circuit designs in the smaller volumes, PLDs have been used. And in order to design or develop any kind of embedded system, microcontrollers becomes the backbone of the embedded system, which is mostly programmable, which is programmed with the help of software engineers. Application of logic circuits. Firstly, applications of logic circuits, you can see anywhere, you take any kind of electronic products, all are designed with the help of logic circuits only. Computers. Firstly, computers, the brain, body, limbs of computer system, everything in it except the peripherals, which are the connection wires, except that one, all are being used or manufactured with the help of this logic circuits. Coming to the embedded systems, the brains that controls the systems. Example, avionics, auto electronics, VCRs, microwaves, all these are different kinds of control systems. These have been designed with the help of logic circuits in the embedded system. DSP, digital signal processing, digital cellular mobile phones which we are using or the laptop which I am right now using to record this video, and digital TVs, everything have been used in order to design this DSP, and this DSP is been manufactured with the help of a logic circuits. Besides computers, logic circuits find the bulk of their application has embedded systems or the brain of enormous variety of products. There are different kinds of varieties where we can use these logic circuits in order to bring up the electronic products. In such systems, they are generally used as a controllers of larger, that's non-logic, example analog or electromechanical systems. So this is different, a vast area where we can find the logic circuits applications. This is one of the logic circuit you can see here now how the sensors have been used, and A to D converters are here. Sensors will be producing an output called as an analog signal. That analog signal will be converted into digital signal. Why? Because the logic circuit will not be understanding the analog signal. It understands only the digital signal, that is 0 and 1. So that's why A to D converters have been required here. This A to D converters, that's the analog to digital converters, will convert it into digital signal and it will be given as input to the logic circuit. That logic circuit will produce some output, and again it will be given to as an input to the D to A. D to A means it's a digital to analog converter. This digital to analog converter will convert the digital signal back to the analog signal, and then it will be given as an input signal to the attenuators, and from there to some control signals. So this is how the entire environment of this electronics is working nowadays. Computers and electricity. So let us see now how this particular gates or the electronic circuits are used in the computers and electricity. So gate is a device that performs a basic operation on electrical signals. What are the signal we supply to the gate? Gate means here, this is one kind of, this is usually called as a logic circuit. So now here there are different kinds of gates. We'll see in the next coming slides. This logic circuit or a gate is a device which will be performing mainly on the electrical signal, which is mostly in the form of this particular 0 and 1 here, which will be converted and given as input as 0 and 1. Then circuit. Gates combined together will form as a more complicated task. So that's why circuit is nothing else but it's a huge design which has been formed with the help of a combination of different kinds of gates. How do we describe the behavior of gates and circuits? So usually the description of the gates and circuits will be done with the help of three methods. Firstly, Boolean expressions, then logic diagrams and truth tables. So these are the three methods where we can understand the working condition of a particular gate or particular circuit. So what is Boolean expression? Using the Boolean algebra, a mathematical notation for expressing two valued logic is called as a Boolean expression. As I told you that y is equal to a plus b, has given an example in the previous slide while discussing about OR logic. So now here y equal to a plus b is called as one of the Boolean expression. So with the help of that particular logic, we need to understand what kind of gate can be used in order to design that particular circuit. So next one is a logic diagram. A logic diagram is nothing else but it's a graphical notation of a particular logic or a gate. It's a graphical representation of a circuit. Each gate has its own symbol. There are different kinds of gates. Each has got its symbols. We'll see it in the coming slides. Truth table. Truth table means it talks about the functionality of a particular gate. It talks about the functionality of a particular circuit. So now how the particular circuit will be working if some inputs have been given to it and what kind of outputs it will be producing. That functionality part is called as a truth table. A table showing all the possible input values and associated output values is called as a truth table. It will be having the complete details about what kind of inputs we are feeding into that particular circuit and what kind of output it is producing out. So this is regarding the truth table. So coming to the logic circuits. Logic circuits. Basically, there are 7 different types of logic circuits, and these 7 different types of logic circuits are being again divided into 3 different parts. Like first one is called as a basic gate, universal gates, and third one is called as an exclusive OR gates. So see now. Usually they call it as an exclusive gates. So now see now. First one, basic gates. Basic gate, first one is NOT, AND and OR. NOT, AND and OR are called as a basic gate. Second one, NAND, N-A-N-D, NAND, N-O-R, NOR. These are called as an universal gates. What does this N stands over here? N means it's a NOT gate. It's a NOT of AND gate. NOT of AND gate is called as a NAND gate. NOT of AND gate is called as a NAND gate. NOT of OR gate is called as an NOR gate. See here now, this particular NOT gate looks like this. This is the NOT gate. What actually NOT gate does is that whatever the input signal you give over here, whatever the signal you give as an input to the NOT gate, it will be always producing the opposite of that signal. It means it will be complementing that signal. You will be getting a exact opposite value for that one. It means that whenever I give an input as a logic 1, your output will be always logic 0. So this is the NOT gate functionality. So now here, what does this NAND gate talks about? NAND gate means it is a NOT of AND gate. Whatever the output you get as an AND gate, that output will be complemented in order to produce another output, that will be the output of a NAND gate. And again, similarly, it works with the NOR gate also. This is called as a universal gate. Why it is called as a universal gate? Why these two gates are called as universal gate? Because with the help of this two gates, NAND gate and NOR gate, we can again reproduce the basic gates and also exclusive OR gates. We can produce different kinds of gates again. So that's why it is called as an universal gates. The next comes is a XOR gate, exclusive OR gate and exclusive NOR gate. These are the three different types of logic gates, which are again classified, which are usually of 7 types, and these are reclassified into 3 types, which is basic gates, universal gates, and exclusive OR gates. NOT gate. So first let us see what is the NOT gate. As I told in the previous slide, the NOT gate is a gate which accepts one input signal that can be 0 or 1, and it returns some output which is opposite to that one. It returns an output which is opposite to that particular gate. So here, whenever it is 0 and 1, the output will be always opposite to that one. It means if you give 0 as an input, your output is going to be 1. If you give 1 as an input to the NOT gate, your output is going to be 0. So let us see the representation of NOT gate. So this is the NOT gate. Here, this is a Boolean expression of a NOT gate. As I told you, if X is the input, then your output will be bar of that one. Whatever the input you give, if y equal to a bar, that means that if input is a, your output is a bar. So X is your expression. X is equal to a bar is your Boolean expression. This is a logic symbol diagram of particular NOT gate as I have drawn in the previous slide. A is the input. A is the input. That input will produce an output which is called as an A bar. That A bar is nothing else but your expression X. You can see the truth table. This is a truth table, as I told. The 3 different things we need in order to design any kind of electronic circuit. First one is called the Boolean expression. Second one is called the logic symbol or representation. Then third one is called as a truth table. So this is the third one. Truth table is the third one. You can see it will be having all the combinational parts. The probability of one input signal will be only 2. You can probably you can give either 1 or 0 as an input to this particular gate. So there is only one probability is there. So that's why if input A is equal to 0, your output X will be always 1. It will be opposite to that one. If input equal to 1, your output will be always 0. So this is how your particular NOT gate will be working. This is a symbol of a NOT gate. NOT gate symbol is this one, where it will be having just like a triangle. At the peak of this triangle, you will be having a bubble. So this is a symbol of a NOT gate, and this is a functionality of a NOT gate. Functionality, what is the functionality of a NOT gate? Whenever you give one input, if it is 0, the output will be 1. If you give an input as 1, your output is going to be 0. It means that it will be complementing it. It will be always producing an opposite output to the signal. This is about NOT gate. Next is a AND gate. Now, AND gate. An AND gate accept 2 inputs. Here for the AND gate, you will be having the 2 inputs. How many inputs will be there? For NOT gate, there will be only 1 input. But when it comes to the rest of the signals, usually they will be having minimum of 2 inputs. So now AND gate accepts 2 input signals. That is, if both are ones, this is a functionality. If both the inputs are 1, whenever the 2 inputs of the AND gates are 1, then output is going to be 1, or else it is going to be 0. It means that if one input A equal to 0 and B equal to 1, your output is going to be 0. Whenever both the inputs A and B is 1, the output is going to be 1. Let us now see the Boolean expression, truth table, and its logic diagram. So see now. The Boolean expression of your AND gate is x is equal to a dot b. It's a multiplication sign. It's a multiplication symbol between that particular a and b. It means it's simply a multiplication of it's a Boolean multiplication. You can see now x equal to a dot b. This is a symbol of an AND gate. AND gate symbol. It has got two inputs a and b. Output is going to be x. So now for this one, if there are two inputs, the probable number of combinations of these two inputs will be 4. So that's why we have written the truth table for the 4 combination of the inputs. If the input is 0 0, as I told that this condition is only applicable whenever both the inputs are 1. If both the inputs are 1, the output is going to be 1, or else it is going to be 0. Means or else means what? Whenever both the inputs are 0, your output is going to be 0. If one input a equal to 0 and b equal to 1, your output is going to be 0. If one input a equal to 1 and b equal to 0, output is 0. Only for this particular state of combination, when both the inputs are 1 and 1, your output is going to be 1. So this is the functionality of an AND gate. This is how the AND gates will be working. AND gate, whenever both the inputs are 1, your output is going to be 1, or else it is going to be 0. So this is the functionality of an AND gate. OR gate. Let us now see the next kind of gate, that's a OR gate. OR gate accepts the two minimum, as I told, all the other gates will be accepting minimum 2 input signals except the NOT gate. NOT gate will be having only one input signal. An OR gate accepts 2 input signals. If the functionality of this OR gate is that if both inputs are 0, the output is 0, or else it is going to be 1. Means what is actually happening here? In the previous case, in the AND gate, it's a multiplication I told. So multiplication means what? 0 into 0 is going to be 0. 0 into 1 is going to be 0. 1 into 0 is going to be 0. So it's a multiplication. But when it comes to the AND gate, it is written that if both are 0, the output is going to be 0. Means what? Here we are going to add the two numbers. OR gate, as I told in the previous slide, OR gate expression is x equal to a plus b. So now let us see the expression, Boolean expression, its symbol and also its truth table. This is a Boolean expression. What is a Boolean expression of OR gate? X equal to a plus b. Thus multiplication, it's an additive symbol. It's a Boolean addition between these two. I'll try to erase that one. Why? Because it becomes another expression. If I put a circle around that plus, again it becomes a different gate representation or notation. So now here it's a plus b. If it's a plus b, plus means what? It's an Boolean expression. It's a Boolean expression of an OR gate. It's an addition between the two input signals, and this is a OR gate symbol. You can see the difference between AND gate and OR gate. This is a different kind of representation is there. It has got two inputs a and b. Whenever you give input a equal to 0, input a equal to 0, again b equal to 0, your output is going to be 0. Except this particular state, all the other states will be having 1. Why? How do we get 1? If 0 plus 0 means 0. Again 0 plus 1. If you give 0 equal to a and b equal to 1, what happens? The output is going to become 1. That is 0 plus 1 equal to 1, 1 plus 1 equal to 1 plus 0 equal to 1, and again as per the Boolean addition, 1 plus 1 is going to be 1. So this is the simple functionality of an OR gate. OR gate will be having two input signal, minimum of two input signal. It can be more than two input signal for these other gates like AND, OR, and different kinds of gates. Minimum should be two input signals. So now except this case, all the other outputs will be 1. So this is a functionality of an OR gate. Next is a XOR gate. An XOR gate accepts two input signals. It means that what is a two input? It's a minimum of two input signals. It can be more than two input signals. Minimum it accepts two input signals. Let us see the functionality. If both are same, if both the input signals are same, output is going to be 0. Means what here? If both the inputs, if a equal to 0 and b equal to 0, your output is going to be 0. Or else if a equal to 1 and b equal to 1, your output is going to be 0. Whenever the inputs are same, the output is going to be 0, or else otherwise what happens? For the other case, if when the both inputs are not same, output is going to be 1. So this is a functionality of an XOR gate. XOR gate functionality is what? If both the inputs are zeros, or sorry, if both the inputs are same, output is going to be 0, or else the output is going to be 1. Now let us see its symbol, expression and truth table. We can see now. That's what I told in the previous one in the OR gate. If I put circle around the plus, it becomes another gate. I told this is that gate. This is an expression of an XOR gate. X equal to A XOR B. You should call it as A XOR B. A XOR B. And this is a symbol. The difference between OR gate and XOR gate is that this one particular line. This one particular line is a difference between the OR gate and XOR gate. So this is how it is notated. If both the inputs are same, see, you can see now this first state both the inputs are same, and again last state both the inputs are same. Whenever the both inputs are same, the output is going to be 0. If both the inputs are same 1 and 1, again output is going to be 0. Or else in the other cases what, whenever the input is 0, A equal to 0 and B equal to 1, or else A equal to 1 and B equal to 0. In this case, output is going to be 1. Only for the first and last state, when A equal to 0 and B equal to 0 and A equal to 1 and B equal to 1, for this case only the output is going to be 0. So this is the functionality of an XOR gate. Next one, you can see here some more details about the XOR gate. Note the difference between XOR gate and OR gate is that they differ only in one input situation. So let us see that when both the input signals are 1, OR gate produces 1 and XOR gate produces 0. Only this one particular signal is different. See now, the truth table. The truth table of XOR gate, you can see now 0, 1, 1, 0. When it comes to the OR gate, you can see all the other three except 0, 0 state, all other having 1, 1, 1 state as an output. But when it comes to this one here, except this last state, there's a difference between XOR and OR gate. XOR is called as an exclusive OR gate. X means it is an exclusive OR gate. Next one, NAND gate. NAND gate accepts two inputs, minimum of two inputs. If both are 1, output is going to be 0, otherwise it's going to be 1. It's an exact opposite to the AND gate. If you see the truth table also, you can understand the difference between AND gate and NAND gate. In that one you have stated differently, but here if you see now, if both inputs are 1, output is going to be 0, otherwise it's going to be 1. But what we have studied in the previous case of AND gate, it's a multiplication I told. So means what, whenever if both the inputs are 1, wherever you find 1 0 anywhere, you can see that CNO. I'll show you the reference CNO. In this AND gate truth table, you have seen that whenever the two inputs are 1, there only you are getting output is going to be 1. In all the other cases, anywhere you find in either for A or B, if you find 0, you will get an output as 0. But when it comes to the NAND gate, it will be completely different. It will be, the truth table will be like this: 1, 1 and 0. What I told, it is an exact opposite I told. NAND means what? Not of AND. So that's why it's a not. It not means what? Not gate will be complementing. Complementing means it will be giving a opposite outputs. If it is 0, it means for the NAND gate it is X bar. I'll keep. Why? Because bar means what? It's an not of AND gate. So X bar, for X bar it will be 1. 0 is output means X bar will be 1. 0 means 1. And only for 1 it is going to be 0. So now let us see the NAND gate. See now the truth table, you can see now, except for the last state, this is a difference. In the previous case it was 0, 0, 0, 1, and here the difference is 1, 1, 0. Exactly, it has complemented the entire thing. The difference is this particular, all the outputs. In the previous, for the AND gate, what was there? It was, for the AND gate it was 0, 0, 0, 0 and it was 1. But it is a NAND gate means what? It's a not of AND gate. So that's why you have got 1, 1, 1, 0. Exact opposite to this outputs. And this is a symbol of this one. How to represent what I told for the NOT gate. NOT gate, it will be having one triangle, and one peak of the triangle will be having one bubble. So now in NAND gate means what? The bubble will be at the output part. So it's a bubble at the AND gate output part. So it's a NAND gate. And this is the symbol, a Boolean expression of a NAND gate. X equal to A dot B bar, A dot B bar. You can either notate like this, or else you can put a complete bar over here. Anything can be used. But for the AND gate, the symbol was only A dot B. For this one, it will be A dot B whole bar. Next, we'll see the NOR gate. NOR gate is a NOT of OR gate. So NOR gate accepts two input signals. If both the inputs are 0, output is going to be 1. Otherwise, the output is going to be 0. It's an exact opposite to the OR gate. You can see the symbol here and its Boolean expression. OR gate expression is what? Expression for the OR logic is A plus B. But since it's a NOT of OR gate, it will be A plus B whole bar. And the symbol you have seen in the previous slides, this is a symbol of OR gate, and this one bubble differentiates OR from NOR. Bubble means it's a NOT. So now whenever you give here symbols, you can see here now it will be exact opposite to the OR gate truth table. The OR gate truth table will be 0, 1, 1 and 1. So this is the truth table of OR gate. For OR gate, exact opposite will be the NOR gate. For OR gate, exact opposite will be the NOR gate, and the truth table you can see here now. Whatever I am writing right now, it is a truth table of an OR gate, and whatever is printed in this box, this part is a truth table of an NOR gate. So this is how the NOR gate works. Review of a logic gates. NOT gate inverts the input signal. This is a very important slide which gives the complete details of all the gates. A NOT gate will invert. Invert means it will be complementing it. Inverts its input signal. An AND gate produces 1 if both the input values are 1. An OR gate produces 0 if both the input values are 0. And XOR gate produces 0 if both the inputs are same. And NAND gate produces 0 if both the inputs are 1. NOR gate produces 1 if both the inputs are 0. So this is what we have studied in the previous slides with the help of its diagrams. So this is regarding the review of logic gates. These are combinational circuits. In this particular slide, you can see the entire logic gates except one extra I have put. This is a buffer. This buffer means buffer is nothing else but whatever you give as an input. It's an exact opposite. The working condition of buffer will be exact opposite to the NOT gate. NOT gate means what? Whatever the input you give, it will be inverting that one or complementing it. But buffer, what does buffer do? It will not invert. Whatever the signal you give as an input, it will send the same signal as an output. So that's a buffering. So now if you give an input 0, the output will be 0. If you give an input 1, the output is going to be 1. So this is regarding the buffer, how the buffer works. So buffer is a circuit, logic circuit, which will be producing the same output as an input signal. Gates. Now let us see gates with multiple inputs. In the previous slide, slides we have seen only gates with 2 inputs. Now in the coming slides, we'll be seeing about gates with multiple inputs. Gates can be designed to accept 3 or more input values. A 3-input AND gate is taken as an example. Here it produces an output of 1 if all the inputs are 1. That's what we have stated in the 2-input AND gate. If the inputs are 1s, the output is going to be 1. So this is the same thing which we have defined with respect to 3 inputs. A 3-input AND gate will produce an output of 1 if all the inputs are 1s. This is an expression of AND gate for the 3 inputs. You can see here now. Here it is like A dot B dot C. Previous it was only A dot B for the 2 inputs. Now it is A dot B dot C. And this is the 3 inputs which have been given for the AND gate, and output is X. So if it's a 3 inputs, the probability combinations will be how many? You can see here now. 1, 2, 3, 4, 5, 6, 7, 8. 8 combinations will be. That means 0 to 7 logics will be. First state is a logic 0, and again up to 7 it will be there. So it will be 8 combinations will be there, and this is a truth table of that particular AND gate. As per the working condition of AND gate is what? If both the inputs, if all the input signals are 1s, the output is going to be 1, or else it will be 0. So only all the input signals are 1 only in the last state. Only in the last state all the inputs are 1. A, B, C are 1. So that's why your output is going to be 1. Or else in all other states it will be 0. This is regarding the 3-input AND gate. Constructing a transistor circuits with the help of a gate. So now let us see how a transistor is being used in order to construct the gates. A transistor. What is a transistor? It is a device which either works as a wire that conducts electricity, or else it works as a resistor that blocks the flow of electricity. So what is a transistor? It's a device which will be working as a conductor in order to conduct the wire, or else it will be working as a resistor in order to block the flow of electricity. It depends upon the whatever the logic you are supplying or whatever the voltage level of input you are giving as an input. So this is regarding the transistor. Transistor means it's a device which will be either conducting that particular signal, electrical signal, or else it will be blocking an electrical signal. It works as a conductor and also it works as a resistor. A transistor has no moving parts, yet acts as a switch. It don't has a moving parts. If you talk about an electrical switch, it will be either in the on state or off state. In the same way, just like a switch, if the transistor can be in the off state or on state. For knowing about the transistor working condition, you can go back to my lecture in my YouTube channel called as Cmos Inverter. In the Cmos Inverter, you can understand how a transistor will be working as a switch, on state and off state. It is made of a semiconductor material. This transistor is made up of semiconductor material, which is neither a particularly good conductor or it is not a particularly good insulator. So it's an in-between insulator and conductor. So transistor is a semiconductor material. It's made with a semiconductor material. Nowadays, transistors have been made with the help of a mostly it is made with the help of semiconductor called as silicon. Constructing transistors. Let us see now how to construct a transistor. A transistor has a three terminal. First of all, a transistor is a three terminal device. It means it has got three terminals. First one is called as a source, second one is called as a base, and emitter. I have shown you a transistor in the previous slides. The base, source, and emitter also I have talked there. Firstly, like a base, source, emitter. Actually, it should be called as like depending upon the type of transistors. I should name it as a, if it is a MOSFET, transistors are again basically two types, BJT and MOSFET. If it's a MOSFET, it will be source. It will be like source. It is becoming difficult for me to writing over here. For if it's a MOSFET, the terminals will be source, gate, and drain. If it's a BJT, that's a bipolar junction transistors. It will be base, emitter, and collector. It should be a collector over here. It's not the source, it has to be collector. It is a collector. So now it's an typing error over here. It should be collector. So now if it is this, what are the terminals we are talking over here? This three terminals. If I strike it off this one, it will be collector, base, and emitter. Emitter typically which is connected to ground wire. Partially ground terminals will be there. Again, so see now. Collector, base, and emitter. This is called as this kind of transistor which has got these three terminals. It's called as a BJT. This is a BJT. BJT is nothing else but it is called as a bipolar junction transistors. Actually, I should call it as a collector over here. It is a collector. The three terminals of a BJT or a bipolar junction transistor. Even this regarding BJT and MOSFETs, there are many lectures I have made as a video. You can look into my channel. It should be like collector, base, and emitter for the BJT, and this is a output where it has been obtained. And for this one, for the MOSFET, it should be source, gate, and drain. It should be source, gate, and drain. These are the three terminals of a MOSFET. So this is regarding how a particular transistor looks like. What are the transistor we have drawn over here? It's a BJT. If electrical signal is grounded, it is allowed to flow through an alternate route to the ground, literally where it can be done no harm. So the main use of this particular ground is to protect the particular device or circuit from the electrification. So see now, this is regarding constructing of gates in order to design any kind of integrated circuits. So now let us see the construction of NOT, NAND, and NOR gates. So this is a particular diagrams how the NOT gate looks like, and this is the NAND gate structure, and this is a NOR gate structure. These kind of combinations, when we apply the inputs, what are the 0 and 1s you are talking about, if you apply that logic inputs, you will be getting an output as a, in the truth table, what are the output you find as a truth table, that is obtained as a V out over here. And this is a construction for the NOR gate, construction, and the same inputs. If you give as a V1 as an input 1A, V2 as an input 2B, the output will be V out. So you can cross check that one also. In order to understand how this transistor works, you are supposed to look into my lecture on Cmos inverter. Combinational circuits. Gates are combined into circuits by using outputs of one gate as an input for another. It means that different kinds of gates have been used in order to combine different kinds of combinational circuits. So see now, this is one of the combinational circuit. We have used here two AND gates. This is AND gate, and two AND gates have been producing some input, given some inputs A and B and B and C, A and C. Depending upon this input, it produces the two outputs. First one produces D as an output. Second one produces E as an output. These two outputs of the two AND gates are given as input to the OR gate. It produces a final output. So this is regarding how a combinational circuit looks like. And for this particular combinational circuit, a truth table has been drawn over here, and you can even cross check that one. You know how the AND gate works and how the OR gate works. If you cross check, you will get the exact output X over here. The input requires 8 rows to describe all the possible inputs. So we are talking about the probability combination. If there are 3 inputs, the probable combination will be 8. So the 8 combinations we have written here, depending upon the 8 combination ABC, we have got the 2 outputs for 2 different AND gates D and E, and that 2 AND gate outputs will become as an input to the OR gate, and OR gate will produce an output. This is that output. This same circuit uses a Boolean equation. What could be the Boolean equation of this one? See now. Up to here, it is A dot B and A dot C. Again, it is plus. OR gate means plus. So now you can see now. Boolean equation can be A dot B plus A dot C. So this will be the final Boolean equation of that particular circuit. A dot B will be B will be this output. D is equal to A dot B. It is A dot B, and for this one, this A dot B, and again for E it will be A dot C. So now A dot B and A dot C are given as an input to the OR gate. That OR gate will produce an output which is plus of this two, that is AB plus AC. So this is what we have got over here. So again, consider the following Boolean equation. For this Boolean equation, we can get the particular truth table. So you can see this is a diagram for this one. A of B plus C. A of B plus C, first OR gate is taken over here. B plus C will be the output of OR gate, and that output is given as an input to the AND gate, and another input for AND gate will be A. So A of B plus C. For this one, by using the truth tables which you have studied in the logic gates, you can apply the functionality and you can get the same truth table outputs. It will be the working experience with this logic gates if you try this one. Combinational circuit and equivalence circuits. Let us see now. Two circuits that produces the same output for identical inputs. So that will be the equivalence. Equivalence means what? We are trying to find out some equivalent circuit for the combinational circuit which produces the same kind of outputs. Boolean algebra allows us to apply probable mathematical principles to help design the circuits. A of B plus C can also be written as AB plus BC. So this is a distributive law which you have studied in the Boolean algebra. So with the help of this Boolean algebra, we can make up the equivalent circuits. The properties of Boolean algebra. These are the Boolean algebra properties you might have studied in the lower sections. Cumulative property. Cumulative means what? AB is equal to BA. 2 into 3 is equal to 3 into 2. Ultimately, we get the same output, that is 6. Next one. This or for OR it will be A plus B or B plus A. So these are the few associative law, descriptive law, identity law, complement law, and De Morgan's law. So these are the few Boolean algebra properties. We have been studying it from the lower sections of the school. Now, let us now study about the adders. What is adder? Adder is a kind of a digital logic circuit which is mainly used for addition of two logics or two signals. So now at digital logic level, addition is performed in binary, that can be in that will be in logic 0 and logic 1. So in order to add these two, we need some digital logic circuits which are called as an adders. addition operations are carried out by special circuits called as an adder. Adders. First, let us see one kind of adder, which is now I'm trying to show you and trying to make you explain what is an half adder. This is a design of an half adder. Half adder, what is this one? We have studied up to now. This is an XOR gate. First, half adder has been designed with the help of XOR gate. It's an XOR gate. The output of XOR gate will be sum, and it will be for this is nothing else but it's an AND gate. So with the help of these two gates, AND gate and XOR gate, we will be designing the adder, and this is the adder circuit, which is it's a two in adder is a half adder is a two input addition circuit. Why? Because if we are talking about half adder means definitely there is another kind of adder called as a full adder. Full adder will be of 3 input for the addition circuit. So now what is the functionality of this adder? The functionality of a XOR gate will be sum. Sum will be producing that whatever functionality of XOR comes out, that will be the sum, and the functionality of an AND gate will be called as an carry, that becomes as an AB. Okay, in order to understand this particular lecture, you kindly look into my lecture regarding this adders. Now, I have made a lecture where I have explained how each and every adder works. There are different kinds of adders and multipliers, but especially on the adders and multipliers, I have made a lecture where you can understand different how this addition, binary addition, can be done. This is a circuit diagram of an half adder. Now full adder. It is a circuit that takes a carry in value. Whatever the carry in comes out, that will become as a third input to the full adder into the account. You can see now. Full adder means what? This part is a one of the adder. This is one of the half adder, and this is another half adder. This is another half adder. So these two half adders are combined in order to get a full adder, and the output of this second half adder is given as an input to the output of second AND gate half adder, and again output of first AND gate output will be given as input to the OR gate. This becomes as a carry out. So now carry in comes as an input to the second half adder. So this is how a full adder circuit looks like, and you can see here the truth table of a full adder clearly. Integrated circuit. What is an integrated circuit? If you are studying here in your plus 2 or 12th class, it's a very important concept as a part of your integrated as a part of your plus 2 or 12th class syllabus. So kindly try to understand this one. Integrated circuit, also called as an chip, a piece of silicon on which multiple gates have been embedded. Different kinds of gates have been embedded on a silicon, that is called as an integrated circuit. Silicon pieces are mounted on a plastic or a ceramic package with pins along with the edges that can be soldered onto the circuit boards or inserted onto proper sockets. As I told you, one of the integrated circuit in the early of this lecture, that is a Nand gate, Nand IC. So integrated circuit is a embedded system or embedded one where you can have different kinds of multiple gates embedded onto that silicon. You might have seen the animation, how this particular animation is, this particular slide is flying off. So in the same way, the integrated circuit industries are in the flying stage. Why? Because it's a very flourishing area where engineers are right now working very hard in order to come up with different kinds of electronic products. It's very high demanded area. Integrated circuit design is a high demanded electronic area where any student can or any aspirant can look into. Integrated circuits are classified into number of gates contained in them, and this abbreviation you can see, this is an era of integration. How an integrated circuit started. SSI, it's a small scale integration where earlier it used to have only 1 to 10 gates integrated. Then next comes the MSI, it's a medium scale integration which has 10 to 100 gates. Then comes a large scale integration which is 100 to it's like 1 lakh gates were been used in order to form this large scale integrated IC. Then next was a very large scale integration which is more than 1 lakh. Even for regarding this special video lecture I have made on the integration era, you can even look into that one. Electronic scientists and inventions in that particular one, and also in the invention era of electronics, I have made a small lecture where I have given even the examples of this 1 to 10 gates, what kind of devices were been made. Wow, 10 to 100, what kind of devices were been made. There are different kind of examples I have given as per the present day electronic products. You can look into that particular lecture also in my YouTube channel. So this is regarding this integrated circuit era, and in more detail you will see it now in the next slide. See now. Integration levels. Level of integration, if it is a small scale integration, it is introduced in 1964 where only 1 to 10 gates were used in order to develop that small scale integrated IC. It's a medium scale integration, means it was introduced in 1968 where 10 to 100 gates were used in order to design or fabricate that particular integrated circuit. Next comes the large scale integration. It is introduced in 1971. 100 to 10,000 gates were used. Next, after large scale integration, it's a very large scale integration, which is usually called as a VLSI, which is introduced in 1980, and more than 10,000 gates have been used in this particular VLSI. After VLSI, in the previous slide I have talked only up to VLSI, but beyond VLSI there are two stages of integration which is right now happening in the present day electronic industries. It's a ULSI. ULSI is called as an ultra large scale integration, where it is introduced in the 1984. This particular ultra large scale integration integrated circuit has got nearly 10 to the power of 6 to 10 to the power of 7 transistors. In the VLSI it was only 10 to the power of 4, but when it comes to the ULSI it is like more than 10 to the power of 6 to 10 to the power of 7 transistors. I'm not talking about the this one gates, I'm talking about the transistors. Now come next is a GSI. GSI is it is called as a giga or giant scale integration. It is introduced in 2000. More than 10 to the power of 7 transistors are used in order to design this GSI integrated circuit. So this particular slide is very important. Why? Because it's an important topic as per the electronic concept of class 12 or 12th class plus 2 syllabus. Now we'll try to see an NAND gate SSI. So this is how it looks like. NAND gate SSI looks like. It's a NAND gate pin diagram which I have already discussed. It's a pin diagram of a NAND gate. Small scale integration. This is called as a small scale integrated circuit. Okay, fine. It's time to bye bye. You can see how it's a bird is flying off. It's bye bye to all. Thank you everyone. I hope you have understood this particular video lecture. I hope it is very clear to you regarding each and every concepts. If you want any kind of interesting videos regarding the electronics, you can comment in the video box where I can come back to you with the new lectures. It will be an encouragement to me. If you come with the comments, it will be an encouragement to me not to make the new lectures. If you understood and if it is very clean and neat for understanding purpose, please encourage me by liking this video or sharing this video and also subscribing to my channel. So like, subscribe and share my channel with all the other so that I get good subscription friends so that I can talk about the electronics to larger section of people. Thank you everyone.